All right, now we're going to be talking about sampling rates, and I cannot stress enough, do not confuse sampling rates with bit depth. Because remember, bit depth is about resolution. Resolution is about how accurate you are making a recording. When you're talking about sample rates, you are talking about frequency. And we'll get to that in a minute. But when you're talking sample rates, we're talking frequency, not resolution, not bit depth. Bit depth is about resolution. Sampling rates are about frequency. All right. Now, samples, as we know, are taken at a regular time interval. The rate of sample measurements is called the sampling rate, or sometimes the sampling frequency. The sampling rate is responsible for the frequency response of the digitized sound. And what does frequency response means? That means, well, as we get into this, the sampling rate determines what frequencies we are capable of recording on that computer. Not talking about how accurately we record those frequencies. We are just saying what frequencies are possible to be recorded on that system, because sampling rate is about frequency. So, what this means is that the number of samples you take per second will determine what frequency range your system, that's a recording system, is able to record. To determine the number of samples that you should take, use what is called the Nyquist theorem. Hint, hint, nudge, nudge, you may need to be able to quote what this is. The Nyquist theorem is very important when it comes to figuring out your sample rate or your sampling frequency, which they mean the same thing. All right, there's a lot of complicated math and things that go into the Nyquist theorem, but the real simple way to look at it is that according to this theorem, whatever the highest reproducible frequency of a digital system will be less than 1/2 the sampling rate. The highest frequency will be less than 1/2 the sampling rate. From what I feel is the easier point of view, is that the way to look at this is the sampling rate must be greater than twice the highest frequency we wish to reproduce. So whatever your target frequency, the highest frequency, so let's say range of human hearing is 20,000 hertz, you're going to need to record or take at a minimum 40,000 samples. And we'll look at this much more here in a second. As I just said, according to the Nyquist theorem, if you wish to record up to 20,000 hertz, the range of human hearing, you need to record at least 40,000 samples. Because the Nyquist theorem states that whatever your highest frequency you wish to record is, you need to record twice that number of samples. Remember that, it's important. Twice the number of samples for the frequency, the highest frequency you wish to be capable of recording. Not to be confused again with bit depth. Bit depth is resolution. That's separate. How accurately are you capable of recording that frequency is what bit depth is about. But being able to record any frequency is based off of the number of samples that you take. All right. However, it's not quite as simple as just taking twice that number of samples. And the reason being is that there are always going to be frequencies above the sampling rate. They don't disappear. And unfortunately, they don't. And what happens is that the frequencies above the Nyquist frequency cause what is called aliasing. It is also called foldover or biasing sometimes. And to combat this aliasing, by aliasing we mean they add, it will negatively influence the frequencies we do hear. Because going back to how harmonics work, upper partials work from the previous lecture, those upper frequencies will affect the amplitude and shape of those lower frequencies. So you could have frequencies in the 20,000 hertz range, 30,000 hertz range, which are outside of human hearing, but they can affect the frequencies that are in the 1700 range that does fall under human hearing. And this is what can cause the aliasing. So you need to use what is called the anti-aliasing filter that you put in front of your AD converter. What this does is that it prevents the frequencies above your maximum Nyquist frequency from ever being sampled in the first place. So you're basically putting a filter. If you're saying the maximum I want to record is 20,000 hertz, then you're going to put a filter there that will block anything 20,001 hertz and above. That filter will just stop them so they can't get through. Problem though that it still isn't that simple. We don't have filters that create what's called a brick wall, where that they completely eliminated any of those unwanted filters. These frequencies will then have what's called a roll-off curve that attenuates the frequencies closest to the cutoff. So we'll look at a diagram here in a second. So by the way, this term legal range, that just means what you deem legal, what you want to have heard, what you want to have recorded in your recording. So there aren't any magic filters that will be completely true cutoff. It kind of, some things will bleed through as you get closer to 20,000. So what you need to take into consideration then when you are taking your samples and recording these things. So if you look down here at this diagram, you'll see here's our 20,000. That's where we wish to reach. We have our frequency filter, the filter, roll-off filter is in here. There is always going to be a little bit of a roll-off that happens there. And so we are going to be picking up some frequencies above 20,000 hertz, which can affect our recording down here. But the more we can roll off, the better it will be. So because of this, as this diagram indicates, that even at a sampling rate of 44.1 hertz, and we'll talk about this more in a second, but this is the CD rate, some of the audible frequencies are attenuated by the filter, but how much is rolled off or attenuated is determined somewhat by the quality of the filter and how steep it goes. This is also called the Q of the filter. All right. Now you may have looked at this and gone, well, wait a minute, if the highest point in human hearing is 20,000 hertz, and by the Nyquist theorem, then that should mean we only need to record 40,000 hertz. Why is CD audio 44.1? By the way, that K just stands for for 1,000. So that's 44,100 samples. The reason you do this is that the higher the sampling rate used, the less noticeable is the impact of the filter on those audible frequencies. because it gives your filter more room to roll those sounds off and not have the frequencies we're looking to work with interfere. This is actually part of the reason why some professionals like sample rates that are significantly above the 44.1K thousand 16-bit Redbook audio standard, which we'll look at in a second. Some go as high as 96,000 or even 192,000 samples, because what they're doing is they're recording all those frequencies way above the range of human hearing, and what they're doing is they're embracing those frequencies, and so that you don't have that weird roll off, and that their hopes are you'll get a much more natural recording by having all those frequencies mixing together. But you're also at that many more samples, your file sizes will become much larger, significantly larger. Because if you're taking 44,100 samples per second, then you double that to 96,000 samples per second, your file sizes have doubled. And double that again, your file sizes. So there is a limit in terms of how much your computer is capable of doing, how accurate your computer is capable of doing at those speeds, but then also you are limited by file size. And so generally speaking, only the really high-end systems will think about recording sample rates that high. All right, I mentioned the Redbook audio standard. Now that's pretty much what we have. I'm done with Nyquist theorem now and sample rates. So again, sample rates are frequencies. If you have questions more about that, doing the reading, I'll send you guys some links to another couple of websites that cover it very well. If you're really having troubles with it, contact me, because I know the frequency part can be a little bit tricky, especially the difference between bit depth and frequency, and I really want to make sure that everybody is understanding that. So if you have any questions on this, please do not hesitate to shoot me an email. But going back to the Redbook audio standard. Redbook, there was a company, or not a company, but a series of researchers that were, when they were first coming up with the standard for digital audio, they actually had a red notebook that they kept all their notes in. So this became the Redbook audio standard. So you hear people talk about Redbook is nothing fancier than that was the notebook, color notebook they used. However, the Redbook audio standard, which is considered CD quality audio, compact disc quality audio, is 44.1K, which is 44,100 samples, 16-bit resolution, 2-channel stereo interleaved file. And we'll talk about what interleaved means here in a second. Now there is another standard, which is the digital video standard, DV. And DV is different. It is 48,000 samples, but still 16-bit stereo interleaved. So the only difference between these two is that Redbook has 44.1, digital has 48K. But they're both 16-bit, they're both stereo interleaved, and these are both more or less your common standards. The Redbook you'll find with CDs, when you download, MP3s even have that same sort of standard, while movies and DVDs and other sort of things will have the 48K standard. It's just sort of the two different worlds that you live in. Now, I mentioned that they are what's called stereo interleaved. Now, not interweaved, but interleaved with an L. Now, what does stereo interleaved mean? It means that the file is a stereo sound file where the data making up the left and right channels are stored together as one continuous block of data. That means that even though technically you have a left channel of audio and a right channel of audio, and you could break them up into two different mono tracks, when it's stereo interleaved, they are recorded together as if they are one file, even though they're two distinct channels of audio. That's why it's leaved instead of weaved, because if it was weaved, they'd be mixed into one channel. But since they are leaved with an L, that means think about leaves of pages in a book. They're just sort of stacked together like pages in a book. They're stacked together and carried together. So when you see something called stereo interleaved, it means you have two distinct channels that are unified together as one file to make it easier to move, to copy it from place to place. That way you don't have to copy two files, you just copy one file. Alright, while we're talking about file formats, in the professional world, there are really kind of two professional formats at play. You have WAV files, which are usually found on PCs, and then you have AIFFs, which are usually found on Macs, and also they are actually the format for audio CDs as well. So AIFF files, if you were to pull directly a music file off of an audio CD, it'd be AIFF. But if you're recording a professional level audio file, which is a minimum 44.1 16-bit, although it could be 44.1 24-bit, it could be 96K 24-bit or whatever, the file format would be a WAV file. Now this is, when we say file format, that is just the sort of packaging that the computer looks at it in. And it is a specific format so that a computer will look at that file and go, oh, that's a WAV file, or oh, that's an AIFF. Because it is a WAV file or because it is an AIFF, the computer then knows how to interpret that data to play the audio back. Be able to take that file and play the audio back. Now there are other formats out there. I'm sure you've heard of MP3s. You have PCM. There's AAC and a host of other kinds out there. They're all have their own different ways of playing back, and the computer needs to be able to understand these. These are all called codecs. If someone asks you what codec are you using for a file, they are talking about what format is it? Is it a AFF? Is it a WAV? Is it MP3? Which I hope not, because it's very compressed. Is it PCM? Is it AAC? Or whatever, because you need to make sure your system knows how to play that codec back. But they're all kind of packaging, that basically just their formats so that the computer knows how to take a look at all those data points and know how to turn that data back into analog audio that we can hear. It does that on anytime computer plays it back. It does it through a process called interpolation. Because remember, what all it is just a series of plots pointed on a graph, and then yes, it's connecting the dots, but the process of connecting those dots essentially is the interpolation. The computer is going through and it is replacing that lost information. It is guessing, making educated guesses based off of that plot and guessing what that lost information is. The easiest way to look at it is that interpolation restores lost data. Because even if you're taking 96,000 samples per second, it's still going to be a gap of information between those samples. So what this does is that it restores those plot points. Now, compressed files like MP3s or what have you, they actually have very complex mathematics so that, let's say you have these plot points. Well, you can actually go back and erase some plot points at specific intervals. And then the computer, based off the mathematics that it knows, it can still go through and plot out that shape of the sine wave based off of very advanced mathematics. And so by removing those points, it's making the file sizes smaller. But then it uses a computer to go back and figure out the difference to restore that lost data, because interpolation restores lost data. That's the biggie. And that's it. Thank you very much.